Okay, silly people, here's the situation. Uh, we have, so this is a Goldstein problem. This is what he calls the equilibrium position for a triatomic molecule. Uh, an equilateral triangle, no, a 45-degree right triangle. 45 degrees here. Um, where the masses are at each corner of the triangle. Um, Here in this particular configuration, all of the masses are the same. Uh, that will help immensely. So I'm just going to call that mass M. And we're meant to find the eigenfrequencies of the problem, yeah? Obtain the secular determinant for the modes of vibration in the plane. Okay, so yeah, we're finding the eigenfrequencies. Whenever you are looking for eigenfrequencies, you know that you're just going to have to be solving this, what they call the secular equation in the book. Uh, Finding the determinant of v sub ij equals omega squared t over 0, or equals to 0, and that's what you're solving for. What is Vij? Well, it's the it's a matrix where the elements are determined by the partial derivatives of V with respect to eta I and eta j. Um, cool. So eta I and eta j being just like different variables that are used for position. Uh, I'm just going to use x and y's here because convention, and they look nicer. So I'm just going to go ahead and start solving for the potential energy then. Um, so the way that I've defined each of these masses and their positions here means that the potential is going to have three terms. It's going to have one of the potential energy that 1 and 2 cause on each other, the potentials that 2 and 3 cause with each other, and the potentials that 1 and 3 cause with each other. Each of these just being spring potentials. So that's not too bad to think about. We can just say that V12 is, and it also says in the problem state that all these spring constants are the same. So K over 2, the determinant, absolute value of the distance between the second mass and the first mass minus the length of the spring squared. Same thing with V13. Very similar form here. And same thing for V23. Let me make that better. R2, R3, minus L squared. They're all absolute values, so the order doesn't really matter. Ooh, I almost made a mistake. It's not the same for V23. Use the freaking Pythagorean theorem to see that the length of that particular spring is the square root of 2L. Nice. Okay, let's go ahead and start expanding these magnitudes then. R2 minus R1. We know how to calculate these. This is just x2 plus L minus x1 squared. That is how I've defined the positions of the masses. And then it's y2 minus y1 here. So the x difference plus the y difference each squared under a radicand. We can expand those polynomials, as painful as that sounds. X2 squared plus L squared plus x1 squared plus 2x2L minus 2x1 x2 plus 2 minus 2lx1. Yeah, that's it. Plus y2 squared plus y1 squared minus 2y1 y2. All under that radicand. Cool. Let's factor out L from that whole equation. In fact, let's factor out, yeah, just factor out L. So we'll have an L on the outside. Everything that wasn't had a factor of L is going to be multiplied by 1 over L squared. So 1 over L squared, that's going to be x2 squared plus x1 squared minus 2x1 x2 plus y2 squared plus y1 squared minus 2y1 y2. And then anything that had a single L term will just be divided by L. So that's plus 1 over L. 2x2 minus 2x1. That's it. And then we had one term that was just L squared, so that's just going to be 1 now. Beautiful. Now, the thing to notice about this whole chicanery that we just did is that in the theory of oscillations, all of these x1 and x2s and y1s and y2s, they're all much smaller than the length of the spring. Small oscillations. So you know what we get to do? We get to say, I don't care about any of that. And so the radicand simplifies by a lot into just L times that stuff from before. 2x1 minus 2x2 backwards. 2, 1 minus plus 1. Awesome. This is the form of a binomial that we can just expand. Because it's a radicand, you have 1 plus a small number. Again, L is larger than x2 or x1, so we can do the binomial expansion without any feelings of grief. So this will end up being L times, what, 1/2 of x1 minus x2 plus 1? x2 minus x1 plus 1. Yeah. Pretty cool stuff going on there. Actually, did I do this wrong? Yeah. This is supposed to have not a factor of... Yeah, because when we did the binomial expansion, that whole second term got divided by 2. But the L remains. We can just factor that L through. Awesome. And that was R2, R1. What we're going to do for R1 and R3 is going to be like pretty much the exact same. I might skip ahead in the video, or I might fast forward this part. All right, we have the 3, 1 term. we did it the same way that we did before. Now I just need the 2, 3 term. Uh, it's going to involve some expansions and some approximations, same as before, but now they're going to be a bit different. So inside the radicand, we're going to have x3 minus x2 minus L squared, y3 plus L minus y2 squared. These are going to be really, really awesome to expand. I'm going to cheat a little bit and only partially expand them, so that we'll just have x3 minus x2 squared plus y3 minus y2 squared, and only focus on the terms which involve L. There are actually going to be 2 L squared terms. There's going to be a minus 2 times L, or just plus 2 times L. We have x3 minus x2. Actually, it's the other way around. x2 minus x3. Yep, and then we have a plus 2L y3 minus y2, all under that lovely radicand. We're going to have to factor out an L again. Might as well just go ahead and factor out the 2 as well, so it's going to be L times square root of 2 out front. And inside the radicand, we have 1 over L squared. All of those polynomial expansions that we don't really care about. Plus 1 plus 2 over L, x2 minus x3 plus y3 minus y2. Sha. Which, under the same approximation as before, those things that we don't care about go away. We have 1 plus 2 over L with the cross terms there. Cha-cha-cha-cha. And then we just binomial expand again. Ooh, I forgot to factor out a 2 somewhere. I forgot to factor out a 2 here and here. So this is going to be 1 and 1. Yes. Okay. So then when we do the binomial expansion, it's going to be L root 2, 1 plus 1 over 2, x2 minus x3 plus y3 minus y2. Yeah, okay. And then when we factor that through, we have L root 2 plus root 2 times x2. There should be an L here. So root 2 over L. Or actually, the L's will cancel out. Yay! Just root 2 over L. No, 1 over root 2. Yeah. 1 over root 2. x2 minus x3 plus y3 minus y2. So let's write out what the potential term between object 3 and 2 are. Remember, it's just k over 2 times the distance between them minus the length of the spring. Root 2L squared, which is when we expand that with our new solution for that particular quantity, 1 over root 2 x2 minus x3 plus y3 minus x2 squared, which is just 1 half x2 minus x3 plus y3 minus y2 squared. So just k over 4 times that stuff squared. Right. Let's write out what the potential with 1 and 2 is. The R12 that we got is all the way up here. This stuff, the L's inside of the squared term are going to cancel out. Bam. So it's actually done away with. That's squared. And the V13 term, similarly, the stuff is going to cancel out. So, what was it? Just y3 minus y1 squared. Yeah. Okay. Putting it all together, the potential is k over 2 times all of it. I'm going to put big braces here. We have x2 minus x1 squared plus y3 minus y1 squared plus 1 half of x2 minus x3 plus y3 minus y2. Cool. Now we can start calculating all these different partial derivatives. We're basically taking a Jacobian of this thing. Let's do, first of all, partial v with respect to x1. We have k over 2 out front. We have 2 times x2 minus x1 multiplied by minus 1. That's it. So it's just k x1 minus x2. Partial squared v by partial x1 squared. That's just going to be k. Nice. Now let's do the partial derivative, the cross term with x1 and x2. It's going to be minus k. I'm just going to do all these cross terms. x1, x3, 0. All of these cross terms are 0. I'm going to write them kind of quickly, so sorry if you missed them. Basically, all of the ones that aren't in this little equation here become 0.
Much later.
My goodness, I hate this problem. So we basically have the first row of the potential energy matrix. We just got to get the next 5. So let's continue doing partial derivatives. Starting with, so cool thing about this is that the potential energy matrix in this case is actually symmetric. I think that has to do with the fact that all the spring constants are the same, or all the masses are the same, or it's just an intrinsic property of the matrix. I'm not sure. But in this case, it's definitely symmetric. So I'm going to skip a few partial derivatives to save time. Going straight to x2, which is going to have k over 2. We're going to have 2 times x2 minus x1 plus x2 minus x3 plus y3 minus y2. Okay. And I'll even simplify that. 2x or 3x2 minus 2x1 plus minus x3 plus y3 minus y2. Okay. So we don't have to do x1. We do have to do the second derivative with respect to x2, which is now 3k over 2. And then with respect to x3 next, which will actually be the same as when we do it with y2. Minus k over 2. Okay. Next one is y3. Actually, let's do y1. It's going to be 0. Which just leaves y3 as positive k over 2. All right. Now let's take the first derivative with respect to x3. Minus k over 2 times x2 minus x3 plus y3 minus y2. The second derivative of that with respect to x3 will be the same as the second derivative of that with respect to y2. It's going to be positive k over 2. And then the second derivative with respect to y1 here is 0. Nothing depends on y1. Then del squared v del x3 del y3 is minus k over 2. Moving right along, I am going to copy the potential again, just so I can look at it. Okay, now del v del y1 is minus k y3 minus y1. Yeah. So you do your second derivative with respect to y1, you get positive k, and you do your second derivative with respect to y3, you get minus k, and then you take the second partial derivative with respect to anything else. We're talking y1, y2 is 0. Then del v del y2 has k over 2 with minus k over 2 times x2 minus x3 plus y3 minus y2. Take the second derivative of that with respect to y2. You'll get a positive k over 2 take the second derivative of that with respect to y3. You'll get negative k over 2. You'll do del v del y3 finally, which has a lot of terms. So it'll be 2y3 minus y1 plus x2 minus x3 plus y3 minus y2. So 3y3 minus 2y1 plus x2 minus x3. You just need the second derivative of that with respect to y3 to finish this out. 3k over 2. All right. So let's do the matrix Vij. The way I'm going to do it is I'm going to do x1, y1, x2, y2, x3, y3 going across and down, right? So that means that the first row of the matrix is k 0 minus k 0 0 0. Then the next row, looking at the y1 stuff, we had del v squared del y1 squared was k. This is going to be 0. We had y1 y3 and y1 y2. So 0 minus k. The rest will follow suit. I'm going to go ahead and fill these out because it is symmetric. It is symmetric. Okay. Looking at the x2 stuff. X2 stuff was 0, 3k over 2, minus k over 2, minus k over 2, k over 2. Okay, so this is 0. This is minus k over 2. This is minus k over 2. This is k over 2. Still don't know what's going on in there. Then the y2 stuff, which was k over 2 minus k over 2 here. So minus k over 2 here. Then the x3 stuff, something 0 something k over 2 and then k over 2 and then minus k over 2. So this is 0 after all. This is k over 2. This is k over 2. This is k over 2. This is minus k over 2. This is minus k over 2. And this is 3k over 2. Okay. Very cool. Now, that is not the simplest form of the matrix. We are allowed to do row operations on these. I'm at least going to put it in row echelon form so that when we do the determinant with the other stuff, it's a lot easier on the multiplication, and I'm also going to make it prettier, so I'm going to write it all again. First, by applying a row transformation to row 3, as row 3 will go to row 3 plus row 1. So 2, 3, 4, 5, 6, 0, 0, 0, 0, 0. Boom, bam, boom, boom, bam. Minus k, 0. 3k over 2 minus k is k over 2. And then everything else is the same. Everything else is the same. 0, 0. 0, 0. 0 minus k, k over 2, minus k over 2, minus k over 2, 3k over 2. All right. Still only doing one operation at a time. Row 6 will go to row 6 plus row 2. Okay. Now that everything is aligned, I am just going to copy stuff down. The only thing that's changing is row 6. And this row is the same. This is 0. This row is actually the same. And then 3k over 2 minus k is k over 2. Right. Now I'm going to do 3 row operations in one step. So row 4 will go to row 4 plus row 3. Row 5 will go to row 5 plus row 3. Row 6 will go to row 6 minus row 3. And then now when this gets reduced, we're going to have some weird shit. Alright. So all these guys are zeros. Yep. K2 minus K2 is 0. Same thing for this guy. That will actually go to minus K. Right? No, it's 0. Yeah. Minus K, so yeah, these are both 0. These are all 0. Bam, bam, bam. And those are all 0. Funny. So 3 diagonal zeros, which means we're going to have a lot of the same eigenfrequencies. 3 of them will be the same. So let's now write the secular equation. I'm going to skip to writing it as a big determinant. K minus omega squared m, all zeros there, 0, K minus omega squared m, minus K, 0, K over 2, all zeros, minus K over 2, minus omega squared m, it's supposed to be minus omega squared m there, and then 0 minus K, K over 2, 0. Whoa. Oh, I skipped a row. My bad. And yeah, that's minus omega squared m. 0, 0 minus k, k over 2, 0, 0 minus omega squared m. That determinant should be equal to 0. And so we only really have omega squared m to the third, so minus omega sixth m cubed times k minus omega squared m squared times k over 2 minus omega squared m. And everything else is 0, is equal to 0. Which means you have 3 eigenfrequencies, 1, 2, 3, that are each 0. What does that mean physically? They still correspond to a normal mode, but this matrix actually kind of takes care of rotational degrees of freedom as well as vibrational ones. So in this case, those 3 different eigenfrequencies correspond to movement, translational, and rotational. So one translational degree of freedom is one of those eigenfrequencies, and then the other 2 are rotational. It's a triangle. It has 2 rotational degrees of freedom. Then the other 2, well, 4 or 5, a couple of them are just root k over m. Right? And then the last one is root k over 2m. So 2 different resonant frequencies after all in terms of vibrational modes, and then a couple 0 ones. Long problem.